For this exercise, I'm going to demonstrate how to write timing code so you can measure how long it takes an algorithm to perform its task. And what we're going to do is we're going to compare the insertion sort versus the quick sort to see which is faster. So to do that, I'm going to write a couple of functions. GetTime, that will retrieve the difference in time between a starting time and a stopping time, the difference between those two, and a generateData function to generate an array. We've seen that before. I'll just add that into our code. And then in our main program, I'll demonstrate how to use the getTime function to measure the time it takes to perform insertion sort versus the time it takes to perform quicksort. To write these functions and to use this code, we're going to need a couple of extra libraries. So I included the header file for the standard lib library, for the time library, and for standard I/O. Now that we've done that, we're ready to write our functions. Let's put them below our sorting functions. The one that is the newest will be getTime, so we're going to write it first. It's going to take two arguments, two time objects, and notice that they have a specialized clock_t data type. That's a special type we use just with time objects. So what we're going to do is we're going to simply take the difference between two times, store that in a variable, and then return that time in milliseconds. So we take the time, multiply it by 10, and divide by a special constant that's built into the time header, clocks per second. So this function is very simple, then we'll demonstrate how to use it in just a moment. We also need a function to generate our data. So to do that, we're going to utilize the random number functions. So sran to reseed our random number generator, and then we write a loop to generate a set of random numbers and put them in the array. And we'll put random numbers in the array from 1 to 100. So there's our statement to generate that range of random numbers, 1 through 100, with rand mod 100 plus 1. Then we close off the loop, and then we close off the function definition. The next step is to write our main program. So let's do that. We want to have a fairly large set of numbers, so we're going to set our size to 10,000 items. So we'll declare our array to hold that many numbers. Then we'll call the genData function to create the set of numbers in the array. Now here's where we begin to time. So the first thing we do is create a clock_t variable, and then we call the clock function, which is part of the time header, and that will give us the current system time. Then we call our sort function. Then we get the system clock again and store it in a variable called in, again of clock_t type. Then we can call our getTime function. Oh, I see we have a little problem here. Let me fix that. And because we're going to run out of room, let's put this on the next line. So we call getTime with endTime first and begin, so that will give us a positive number, and then we inline. Now we want to do the very same thing with quicksort. So we're going to generate a new set of data because our array is now sorted. Then get the beginning time with the clock function. Call quicksort with its parameters. Then get the ending time, and then display the result. So that should be all we need. So let's build and run the program. Okay, so you can see there's quite a bit of difference. The insertion sort took 4.44 milliseconds. This is in milliseconds. We would probably add that to our result. In fact, let's do that right here, just to be on the safe side. Just like that. And then the quicksort took 0.02. Let's build and run again. All right, so this time 5.25 and 0.02. Let's run it again. We can just run, we don't have to build and run. Insertion sort time varies a little bit, not much. Quicksort is very stable in the time. I'll do it one more time. Insertion sort took 4.57 milliseconds, and quicksort took, again, 0.02 milliseconds. So to recap, we wrote a getTime function that simply took two system times of clock_t type, computed the difference, and then returned that as milliseconds. Ticks times 10 divided by clocks per second. Then to time the code, we get the beginning time, perform the algorithm, and then get the ending time, and then display it. And we did that once for insertion sort and a second time for quicksort. And as we saw, quicksort is always many times faster than insertion sort. So for large data sets, you should always use a quicksort algorithm versus a insertion sort or one of the other less efficient sorts. But keep in mind that nowadays most systems have built-in sorts, and the most efficient sort is usually used to implement that system sort, so you don't have to worry about it. But with that, we're finished with the exercise, and we're finished with our chapter on non-STL algorithms.